Hi, everybody. This is Professor Ross, and we're here to talk about how to do inference for a single quantitative variable. So let's pull up some notes here. And one of our main goals in this unit is to recognize potential biases in sampling, including our surveys. So when we want to do a inference, we always want to make sure that whatever sample we have has not come from a biased procedure, and so that whatever estimation we're doing from our sample is representative of the population. So we'll keep that in mind throughout. The main idea for doing inference with a single quantitative variable is that we can use similar procedures with sample means as we've used with sample proportions. So now we'll talk about scenarios where we have a quantitative variable and we'll be looking at a mean versus when we had a categorical variable and we looked at a proportion. But for the most part, the procedures are actually going to turn out to be pretty similar. We can examine a claim about a population mean, and we use this Greek letter to represent the population mean. Mu is how we pronounce that Greek letter. Recall with proportions, we use the Greek letter pi. Now we're going to be using the Greek letter mu for mean. That's the Greek letter m. So we'll have some claim about that, a hypothesis with a claim about what mu is. And we'll seek to find the probability of getting the mean from our sample, or more extreme, of course, if the claim were true. That's the p-value. We can still use the 3S strategy. We can still use p-values and standardized statistics. So there are two ways to approach doing inference, a simulation-based approach and a theory-based approach. We'll actually find in this case, trying to use the three S's and a simulation-based approach is more challenging, and often we try to turn to the theory-based approach in this scenario. Let's talk about a simulation-based approach. What we need in order to really do the simulation is we need all the data from the population. That means we would need to do a census and get data from every individual in the population, which in some sense would defeat the purpose of even trying to do inference. So that's the big challenge to doing a simulation-based approach. Assuming we could do this and we did have all the data, then we could simulate drawing random samples from the data, and we could calculate simulated means from those samples and look at the distribution of those x bars of those means. And we could see how likely it was for an x bar like ours from our sample to appear. Uh, so as I mentioned, there's this big hurdle of needing all the data from the population. So there's a way around that with a type of simulation approach called bootstrapping. We're not going to get into that in this course, but just so that you know, that is one way to do it. But the other way to approach it is to not use simulation-based approach at all. And that's basically what we'll do in this course. We'll say, let's not do simulation-based approach. Instead, let's do a theory-based approach. Now, a theory-based approach, there are a few things we need there. We need to have a large population. And for the most part, we're always going to have that. We also need to have a sample size greater than or equal to 20, and the sample should not be skewed. So these are the key requirements that we have to meet. We have to have a sample size that's bigger than 20. If you're right at 20, that's probably okay as well. But if we have samples that are smaller than that, it turns out that the central limit theorem, the main governing theorem for doing a theory-based approach, does not function well anymore. And the results we would get would not be very reliable. So we need to have a big sample size, and then our sample can't be too weird. If it has outliers or a long tail in one direction or the other, then we run into troubles. Now, saying the sample should not be skewed doesn't mean it has to be perfectly symmetric or no hint of a tail in any direction, but it just means we shouldn't have some strong skew one way or the other or some big outliers. Those can cause a lot of troubles when we're trying to use means in our calculation. Assuming we have those things, then the central limit theorem says that the null distribution would turn out to be normal. This is essentially telling us what we would get from a simulation-based approach. Also, the null distribution would be centered at mu, just as we saw the null distributions for proportions were always centered at pi. With a quantitative variable, the null distributions are always centered at mu, the mean of the population, as hypothesized in the null hypothesis. And here comes the key part. The central limit theorem says we can estimate the standard deviation of the null distribution with this formula. S is the standard deviation of the sample, n is the sample size. So we would take S divided by the square root of n, and that would give us that spread of that normal null distribution that would turn out something like this. It would help us know how spread out it is. How does that help us? Well, if we have a result somewhere out in here, if we know the standard deviation, we can tell what that standardized statistic is, how many standard deviations away, and then that'll help us get a sense of how likely or unlikely our result is and how much evidence we have against the null hypothesis. The null distribution we call a t distribution in this scenario. It's a lot like a normal distribution, but we call it a t distribution. It has slightly different shape. And the standardized statistic, we call a t statistic instead of calling a z statistic. But we would calculate the t statistic in the exact same way. Um, we would, the t statistic is still our statistic, which in this case is x bar minus the mean of the null distribution, which in this case is mu, and divided by the standard deviation of the null, which is what that little formula I circled there is all about. So to calculate it, we'd have x bar minus mu divided by this guy here, s divided by the square root of n. I'm not going to ask you to memorize that formula. If you ever want to use it, I'm happy to provide it for you. But mainly, we're going to use technology to find t statistics. What I wanted to show you with writing this down here is this is the exact same formula as what we use with proportions. Um, these particulars are specific to the scenario, but the formula itself is the same thing as before. Let's try this out as an example. Do Maryville College students text a lot? A Nielsen survey claims that the average American teenager sends 111 texts per day. I don't know if I've sent 111 texts in my lifetime, but anyways, that's what they claim they found. So, and somehow I have the wrong numbers here. I typed those in wrong. Apologies. So the null hypothesis is that mu, the average number of texts, is the same as what Nielsen claims, but the average number of texts of Maryville College students, 111. And alternatively, mu is not 111. Do we do something different than what the Nielsen survey found? Let's take a look at some data from a sample. A survey of 378 Maryville College students over the last few years indicated a mean of 91.7 texts with a standard deviation of 183.5. So this is from our sample. And so this is our X bar here, 91.7. And this is our S, our standard deviation from our sample, 183.5. How can we use a theory-based approach to see how we feel about this null hypothesis that the mean number of texts at Maryville College is 111? We can use the applet, plug in our information, find a t statistic and p-value, and make a conclusion. So let's go ahead and jump over to the applet and take a look at how we can do this. We have a bunch of applets to choose from. If we're going to do a theory-based approach, the theory-based inference applet is a good place to go. We one thing to make sure you check first when you're using this applet is what scenario that it says to use, and we are talking about one mean, the mean number of texts rather than one proportion. We had a sample size of 378 students and a mean of 91.7 texts. and a standard deviation that was a little over 183.5. Okay, quite a bit over that. Okay, so I'll put that information in there. I'll hit calculate. It'll give me this graph, not the most useful graph. It shows me where the mean was a little below 100. It shows me how spread out my results were, pretty spread out. In order to do a test of significance, check on the test of significance box. And then you'll note that by default, it puts mu equals 0 as the null hypothesis. This is where we want to put in that claim that we're testing, 111. When I put it in one box, it automatically changes the other box. And but I do want to make sure this matches. I decided to do a two-tailed test because I didn't know if Maryville College students would be higher or lower than that. We're going to hit calculate and we get a picture here. This is what the central limit theorem would predict the null distribution would look like, T distribution. And here's our result down here below the mean of the null hypothesis 111. We're down here a little bit below that. You can see that the spread of our null distribution is a little over 9. And that comes from that formula S, 183.5 divided by the square root of n, 378. Scrolling down, we can see our standardized statistic, t is negative 2.04, and our p-value 0.04. What are these telling us? Standardized statistic is saying our result was just about exactly 2 standard deviations below the mean of the the mean from the null hypothesis, 111. So 1 standard deviation, that's very typical distance from the mean. 2 standard deviations is twice as far away. We're seeing something that's beyond 2 standard deviations, just beyond. So we're talking about strong evidence against the null. Does that line up with the p-value? P-value below 0.05. Once again, strong evidence against the null. So both of those agree. We have strong evidence against the null hypothesis. The null claim was that Maryville College students text on average 111 texts per day. We are finding a statistically significantly lower amount of texting going on, somewhere much more around 90. 91.7 was our average. So that's how we can conduct a test of significance with a mean in a theory-based approach. A couple more quick comments. We've been talking about means, but another measure of center that is commonly used is medians. Why means why means in this scenario? Why not medians? When is it appropriate to use medians and when means? We usually use means, but sometimes medians are preferable. Why? The key is the resistance to the effect of outliers. So we calculate the median by finding the middle number. If I have a bunch of numbers here, each circle represents a number 1, 2, 2, 3, 3, 3, 4, 4, and 10. The median just counts to the middle. So I've got, I count off 1 on the ends, and then another one, and then another one, and then I'd make my way to the middle here, and my middle number would be 3. That's the median. You'll note that this first one here, I would have checked off it were at 10 or at 6 or at 1,000. It doesn't really matter where it is. I just check it off as I count my way toward the middle. It's resistant to this being an outlier. It doesn't matter how far out it is. It just checks it off as we make our way toward the middle. Now, on the other hand, the mean is the sum of the values divided by the number of values. Here, if I add up all these values, the 10 is going to add up into that sum in a very important way, right? When I add 10 plus 4 plus 4, let's see here, that would be 10, 14, 18, and 19, and 3 more is 20. 4 more is 23, plus 1, 2, 3, 4, 12 more. That's 35, right? In my sum of values of 35, that 10 played a big role. If it had only been 5, my sum would have been what, 20? No, excuse me, 30. So it makes a big difference whether this is 10 or 5 or 100. That changes that number a lot, which means it changes the total for the mean quite a bit. How many do I have here? 1, 2, 3, 4, 5, 6, 10. So my mean is 3.5. A big question is which of these, 3 or 3.5, gives us a better picture of what's typical in this data? And for the most part, we should agree that the median does a better job here. The 3.5 is up here above most of the data and pulled up here by this 10, whereas the median has not been affected by that 10 and gives us a measure of center that's more truly toward the center of the data. So if we change that 10 to a 5, as I mentioned, this guy here still stays 3 because the middle is still there. This guy here would have changed to 30 divided by 10, or 3. It's the mean that changes when we have an outlier, and so the mean is not resistant to the outliers. Now, what's that all about? When we're doing some statistics and we have an outlier, we have to be very careful about using the mean because it can get thrown off by an outlier. And if we're looking at data and saying, hey, my data's got a big outlier, or maybe it has a real strong skew, a tail in one direction or the other, we may choose to use procedures that use the median rather than the mean. We haven't talked about procedures like that. They're out there. We won't get into them a lot in this course, but it's good for you to know that that's something to be aware of and be thinking about. Whenever you have outliers, you got to be wary about using them.